you very much again for being here to this session. A lot more people than thought. Nice. So the next speaker is Ludovic Sacchelli.
I don't know how to do this.
He's going to start soon in Nice, in Riyadh, but for now he's at Dario in Lyon. And so he's going to speak to us about the joint work on auditionary cortex, auditory cortex model for sound processing.
Thank you, Dario. Thank you to the organizers of this very nice conference. Thank you for everyone for coming to the early morning session. Yes, I want to talk to you about work we did with Asswad, Boscain, Dario, Prandi, and Giuseppina, Turco on a problem of auditory cortex model. So we modelize the auditory cortex for some ideas of sound processing. And basically, the idea behind this work was to try to capitalize on the successes of subremant geometry in the field of imaging painting. So with the construction of bio-inspired methods built on the subremant structure that Petito described yesterday on the visual cortex. And so what we want to do is to try to understand the heuristics of this method and apply them to a new problem, which is basically sound processing for us. And we'll see what we have to do. So we have the very successful algorithms, and they rely on the structure of the visual cortex. And what we have to understand is what can we bring from the visual cortex to maybe the auditory cortex, and understand also what we cannot bring, which is to say how to understand the fact that the visual cortex is going to be sensitive to some orientation notion that doesn't make a ton of sense for sounds. Okay, so I'm going to talk about basically the ideas behind the algorithm or the structure of V1, the modeling of V1, and we'll see how we can translate these ideas for sound. So, as Petito explained yesterday, it was discovered, let's say, 50, 60 years ago that neurons in V1 are sensitive to position and orientation of edges. And so you have this structure, this three-dimensional structure for the primary visual cortex.
No question.
Later.
Please, sir, turn off your microphone because we are presenting. Yeah.
Okay. Yes, so we have basically a mathematical model for sensitivity in the visual cortex, which is basically representing this visual cortex as the set of sensitivities, which will be a manifold, which is basically R2 cross P1, so R2 for positions and P1s for orientations. And basically what happens, what you can represent mathematically is that smooth curves in R2 will be lifted to the space R2 cross P1 by addition of this tangent orientation data. And so how can we translate that into a structure? Well, as Petito presented, and we have the two other culprits for this Chiti-Petito-Sarti model of V1, which is basically endowing this structure of lift to R2 cross P1 with a subremant structure. And basically, the lift endows naturally the 3D space with a structure that, for me, is easier to represent as a control system or in the control system formalism, which is saying that we have a dynamical system with degrees of freedom. And this dynamical system here will be the one that I'm interested in, which translates the fact that you have orientation and position, which are connected according to some rules, so non rules.
Да, я хотел спросить, но что-то не получилось.
Yeah.
So you got muted. Okay, so how do you go from this structure to cortical-inspired imaging painting? Basically, it's a shift from subremant structure to a diffusion process. Basically, you can imagine that if you represent the structure of connections in the visual cortex with your subdomain structure, then you can say activations in the subdomain, in this subdomain structure follow some random walks, which in macro scale translates to diffusions. And so basically you have your algorithm, which will take a corrupted image and apply some diffusion according to this structure. And then you can basically use this information from the diffusion to recover a reconstructed image. And so that's the outline I want to follow for my cortical inspired algorithm, which is to say I have a signal that is going to be lifted. The lift implies a subdomain structure or some kind of structure, control system structure. This structure then implies a diffusion, and then we can apply this diffusion to a reconstruction algorithm. So the question is, how can we translate this outline to sound processing? Okay, so we have to think about the auditory system for a minute. It's not the same as the visual system, but there are similarities. So basically, sounds enter your ear and then are basically in real time frequency decomposed. They follow a frequency decomposition in the cochlea, which is to say that the cochlea is going to be organized in this like shell, snail shell shape, which allows for frequency decomposition at the basal and apical region. And then this information of a signal that is real-time frequency decomposed is fed to the auditory cortex. And so the auditory cortex is going to see a signal that is in the time frequency domain. So there is a very simple way mathematically to make a time frequency decomposition. It is following the short-time Fourier transform. And that's the formalism we're going to follow, even if it's not the most precise from the modeling of the ear. Okay, so you have this time frequency signal, and basically, so what happens is that you have a spectrogram that is fed to the auditory cortex. So the auditory cortex is fed a two-dimensional signal depending on time and frequency. And still, in these time frequency signals, you can see some variational information. It's not the same as an image. So when you look at lifting an image, the information you're trying to gather is the orientation of edges. And this transformation or this lift should agree with the fact that when you rotate or translate an image in this way, basically the orientation should follow the same rule. Like you should commute with these rotations and translations. But it's not the same with time frequency signals, because time frequency signals need to stay time frequency signals for it to make sense. So we have to drop the idea of orientation and find some variational information that is not orientation, but respect the fact that time is basically an anchor for us. So time goes towards the future at the speed of 1 second per second, and we have to respect that and say that the first order information that we are going to gather from this signal is going to be the what we call instantaneous chirpiness of the sound, which is basically the derivative of the frequency. And so what we're going to do is that assume that our model for the auditory cortex is going to be modeled as a set omega and nu, where omega is the frequency and nu is the instantaneous chirpiness given by the derivative of omega. So what is the lift and the induced structure? So the lift is when you have a curve t associates omega of t in the time frequency domain, you associate it with a lift, which is going to take t and give you omega of t, d omega dt. And so from this lift, you can recover a control system structure, which is a dynamical system with degrees of freedom, except now you have 1 degree of freedom, which corresponds to the fact that nu dot is free. And so from this dynamical system with degree of freedom, we associate a PDE, which is now not a pure diffusion, but a Fokker-Planck equation. which has the good taste of being hypoelliptic and admitting a kernel that we will exploit for our processing. Okay, so we build a sound processing algorithm on that structure, which is to say that we take a sound, we apply a short time Fourier transform to that sound to get the time frequency signal, and then we lift it in a way that I will explain to the set T omega and nu, so adding chirpiness into the signal. And then we apply a processing, a diffusion that is inspired by the auditory cortex and the structures that we know. And finally, we project it back to sound signal. Okay, so I'm going to explain basically how everything happens here. So short-time Fourier transform, I hope, is not an issue. But we'll talk about the lift procedure, the signal processing, and then the projection. Okay, so the lift is basically saying that we're going to take a signal in the time frequency domain. We add the chirpiness component by basically saying that we're going to lift it according to this rule, which basically translates that we look at the heat map of the absolute value of our signal, capital S, and we lift the level sets of this function. And so adding this information of the lift of the level sets then allows to construct a surface on which we put the value of S. And then we apply some processing inspired by the auditory cortex. And so basically what we use are a model for neuronal dynamics obtained by neural mean field equations. So basically these are WilsonCowan equations, which have the following features, basically saying that the first line is basically a low pass filter where you have your input I, which is the sound that has been lifted. And then you have some internal connections, and the effect of these internal connections is given basically by the diffusion term here that appears as a kernel for the equations we gave earlier. Okay, then when we apply this signal, this processing, we can basically project everything back to a sound. And what we did was make sure that if you start with a sound, you apply this algorithm, you have a sound in the end. Okay, so everything works well. So I'm going to finish with some discussions of the algorithm. So what can we obtain with this algorithm? So these are two very synthetic sounds that follow that should represent some properties of the algorithm. And the properties we are looking for, first of all, here you have a time frequency signal where basically you have a single frequency that is augmenting linearly in time. And we cut a piece of that frequency, of that signal. And what happens is that if you apply the reconstruction, what you get is a single chirp uninterrupted. The other interesting feature of such algorithms is that when you have two chirps that should cross in the future, the effect of the algorithm, because we have a lift, is that they will not interact because they're not assumed to interact. When you have two chirps, they should just sum linearly, and that's basically the effect we obtain with these diffusions. Okay. So let me just give a final discussion of bringing these ideas towards speech sounds. So one major issue that we may face with chirpiness is that when we were talking about orientation in vision, orientation was a bounded quantity. Orientation is in 0 pi, so you don't care about discretizing that set. The problem is chirpiness, a priori, should not be bounded because it's the slope of a curve in from R to R. However, when we look at databases of speech sounds and words, what happens is that chirpiness is actually very localized. and we basically explore the distribution that you get from on chirpiness. And it's very localized. So we can basically cut off the end of the chirpiness set, and everything works well. We also happen to recover some nice properties of speech recognition, which is to say that the processing shows some stability to additive noise perturbation. So this is kind of expected because of the way the diffusion works. But also we can see that the chirpiness is not going to be lost by adding perturbative noise. So this is kind of robust to that particular side. Okay, so let me give a conclusion. So basically what I was interested in was presenting you a framework that was inspired by image processing and subliminal modeling of the visual cortex, and basically adapting that framework to sound reconstruction by considering the differences and the similarities between the visual and auditory cortices. So what we do is we have a lift that adds instantaneous chirpiness to a time frequency signal. And so we have from a 2D to a 3D space. Then the structure that is induced by this lift translates to some specific diffusion. And then we use these diffusions in WilsonCowan equations or simulations of WilsonCowan equations that model neuronal dynamics to obtain some kind of treatment of the signal. And we wish to apply these ideas to synthetic sounds, from synthetic sounds to speech processing and this kind of problems. And this is encouraging, I think. Thank you for your attention.
For some quick questions. Eric?
I have a question regarding the lifting to this chirpiness parameter.
Yeah.
Can you explain it a bit more in these senses? Chirpiness was a change of frequency. You have the frequency of the lifting, or the equation for the lifting. Can you show that?
Yeah. This one, right?
Yeah, this one. Can you give some information also regarding going from the heat map to the level steps and the width of the steps?
I mean, it's really very much, I mean, basically what we solve is this equation here for new, okay? What we have the heat map of the absolute value of our time frequency signal. We compute, I would say, we compute approximations of these partial derivatives, and we solve for new. So there may be issues where you don't have solutions and everything, but we reject all the edge cases that we don't need to consider, and works very well nevertheless. And what we do basically is saying that you have your heat map, and your heat map has level sets, and level sets are curves, or you can assume that they are curves in the sense that you can see them as a collection of graphs from R to R. And then you lift all these graphs by adding the derivative of the graph, so the slope, as a third coordinate. And so you have this lift into a three-dimensional space.
Okay, thank you. That's helpful. And then for the top equation, it's like you have this constraint mu is dw over dt, and it's weighted with the normal S. Is that how I should see it? Like you have multiple frequencies. Yeah, you have a heat map for frequencies, and that's how you weight it.
No, you treat it just like a heat map over the set, and I don't.
Okay, no, that's just good.
Yes, yes.
You have a quick question, Sandro?
So I think we are very late. I have a very quick question, but we are very late, I see.
Yeah, but
so if you look at the statistic of co-occurrences of edges in visual images, in natural images, you see that it is in the SE2 group.
Mm-hmm.
Okay. Did you check that the data, that the statistics of your data is really in the Heisenberg group?
Not really, but I think it's a good idea to look into it.
Thank you so much.
Thank you.